Assalamu alaikum. Today I'll be talking about the case study of my topic, that is design and analysis of high frequency transformers. My name is Agha Dilawar Haider Mirza and I'm from the Department of DSSE Electrical Engineering. The course title for which I'll be doing the case study is Electric Machines. So let us proceed. Why choose high frequency transformers? As per their name, they operate at much higher frequencies. The primary difference is that, as the name implies, they operate at much higher frequencies, while most line voltages transformers operate at 50 or 60 Hz. High frequency transformers use frequencies from 20 kHz to over 1 MHz. Operating at a higher frequency has many benefits, the first of which is size. For any given power rating, the higher the frequency, the smaller the transformer can be. Second, because the transformer is smaller, less copper wire is needed, thus reducing their losses and helping to make the transformer more efficient. High frequency transformers are used for a wide range of advanced applications, both large and small. From powering personal computers to providing electricity to homes and commercial property, the product can also be used for alternative energy inverters, electronic switching devices, military power supplies, LED lighting, plasma generation, and personal electronics. Now I'll move on and discuss about high frequency transformers a bit more. Everything comes with its cons, and so high frequency transformers also. There are three problems with high frequency transformers. Its AC resistance, its leakage inductance, and its core losses and winding losses. This slide will discuss the problems that we encounter in high frequency transformers. The first of which is AC resistance. AC resistance is due to proximity effect. So let me tell you about the proximity effect and skin effect. Due to magnetic fields of the other nearby conductors, the current in a conductor tends to follow in an unwanted patterns, usually getting constrained to a part of the conductor. This effect is known as proximity effect. Skin effects are caused by the tendency of high frequency currents to flow on the surface of conductors. This effect causes an increase in the AC resistance of the inductor. Foil windings have superior skin infiltration depth. The AC current doesn't simply stream on the external surface of the wire. However, it increments if foil thickness increments for high power transformers. Dobel's work is generally used to compute the AC resistance factor for a given conductor. In the further slide, we'll be discussing how that to diminish proximity effect, the factor should be near to 1. The next of which is leakage inductance. Not all the magnetic flux generated by an AC current excitation in the primary winding of a transformer follows the magnetic core and links with the secondary winding. The flux linkage between the two windings or part of the same winding is never perfect. Some flux will leak from the core and return by air winding layers and insulation layers, causing imperfect coupling to the secondary winding. Frequency dependent leakage inductance is regularly observed. High frequency eddy current impacts causes a decrease in leakage inductance. The proximity impact between adjacent layers is answerable for the decrease of leakage inductance. Leakage inductance happens when the secondary and primary coils are not entirely connected through polarization of dipoles or magnetization, as studied in our course. It very well may be derived that broad interleaving of the primary and secondary sides brings out a reduced leakage inductance. The next of which is core losses. Core loss is the eddy current loss, which is due to the induced voltage within the magnetic core in the same way that it is induced across the windings as explained by Faraday's law. This voltage produces current that flow in a resistive environment. For that reason, magnetic cores are made with laminations which reduce the trajectory of the currents. The major percent of the total core losses is due to the hysteresis and eddy current losses. The rest is attributed to the residual losses, which are losses with a more complex mechanism and often related to relaxation process in the magnetic material. We'll move on and we'll see that do we have some solutions for this? Yes. For sinusoidal currents, current density is exponentially decaying function of distance into the conductor which with characteristic length known as the penetration depth or skin depth. To diminish the proximity impact, as I discussed earlier, it should be near to 1. The following formula is the ratio of the AC resistance of a transformer to the DC resistance of a transformer, which is derived with the help of Dowell's expression. The skin depth can be calculated from this formula. Copper foils can be introduced instead of a circular round conductor. This is due to the reason that copper foils have inheritance of more penetration depth. Leakage inductance. Leakage inductance is an inductive element in a transformer that results from the imperfect magnetic linking of one winding to another. Leakage inductance plays a critical role in switching mode power supply design. It makes the switching current at the device vary at a slower rate and increases the commutation time between output diodes. Moreover, the stored energy in the leakage inductance leads to the voltage spikes in the switches. Consequently, it creates electromagnetic interference problems, increases switching losses, and reduces power efficiency. To describe it more, I would say at higher frequency, the current will in general focus on the surface of the conductors and subsequently equally lessens the cross-sectional region of the conductors wherein the leakage energy is stored. This implies that the leakage inductance is diminished with the expanding frequency. Looking further into leakage inductance, we see leakage inductance at 1 MHz for different configurations from A to D. The configurations are given as follows. Use this formula and obtain this graph. These figures can be referred to the case study where I have linked to the research papers I have gotten from the data I've gotten from. Case A is a non-interleaved winding configuration where 6 turns with one winding proportion are wound for both the primary and secondary sides. Case B is a partially interleaved winding configuration where 6 turns with 3 windings portion are wound for both the primary and secondary sides. Case C and Case D are fully interleaved with winding configuration where 6 turns with 6 winding proportions are wound for both the primary and secondary sides. Leakage inductance calculations and simulations for the 4 cases at 1 MHz are shown on this side. We can see the values of the leakage inductances and compare it. Solutions to the core losses. Not all the magnetic flux generated by AC current excitation in the primary winding of a transformer follows the magnetic core and links with the secondary winding. The flux linkage between 2 windings or the part of the same winding is never perfect. Some flux will leak from the core and return by the winding losses and insulation, causing an imperfect coupling to the secondary winding. High frequency, high force transformers utilizing power electronic converters are every now and again exposed to sinusoidal excitations. As we all know, impacts of core losses in these transformers will be seen by broad arbitrary waveform. This transformer core should work at higher temperatures brought about by more significant levels of power density and loss density. Hence, the thermal stability of the material is of the extraordinary concern. So what's the conclusion? We saw that different parameters affected the efficiency of the transformer, but the mathematical model provided and which gives some results showed that the efficiency can be increased. We saw that the proximity effect caused most loss which includes AC resistance and leakage inductance. We also saw how skin effect can cause losses in a transformer and can be reduced. Thank you so much.